Welcome back, geometry students. We are on our video number 4 for quadratics. And we're going to talk a little bit about radicals here and then talk a little bit about solving using radicals. So I talked a little bit about this in class, and so you may have learned this in Algebra 1 a little bit, but I just kind of wanted to review how to simplify radicals, how to rationalize, how to, just kind of go through some of the basics with radical work. So let's look at something like root 48. And so there are a couple ways that I've learned how to reduce a radical. And so the most common is kind of looking for the largest perfect square that can go into 48. And so in this scenario, again, it might be helpful if you kind of write down what the perfect squares are. So that way you can kind of think about like what, if you're dividing by these numbers, which one goes in there. So like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and 9 squared. So we'll kind of go up to there. So if you're looking for which number kind of, there's 1, 4, 9, 16, 25, which number goes into 48? And so the largest perfect square that goes into 48 would be 16. And in fact, it's 16 times 3 that equals 48. And so what this really is, this is a perfect square, right? And so what we're really doing here is we're rewriting this as root 16 times root 3. That's ultimately what we're doing here. And all we're doing then is just reducing root 16 to 4, and then we have 4 root 3. Another option of doing this, another way, I should say, of doing this, is to kind of use just like the prime factorization. And so what I mean by that is, I'll just put or. So here's another option. Let's say you couldn't think of like what the largest perfect square is that goes into 48. And that's okay, because sometimes, especially if you're trying to do this quickly, you may not, or if you don't have a calculator handy or whatever. So a lot of times what I'll do is just, especially if it's even, I'll just find any number that goes into 48, and preferably a prime number, but we'll look at it. So in other words, like if it's 48, I always kind of divide it by 2, because if it's an even number, we know that it's always divisible by 2. So I had 2 and 24. And then you keep breaking this down. So I'll do 2 and 12. And then I'll break this down into 2 and 6. And I'll break this down into 2 and 3. You break this down into what we call prime factorization. In other words, if I multiplied 2 times 2 times 2 times 2 times 3, I would get 48, or root 48 in this case. So to simplify this, because we're looking for perfect squares are kind of 2 of the same value. So 2 and 2 gives me a perfect square. 2 and 2 gives me a perfect square. Because we know that 2 and 2 is actually just 4, right? And the square root of 4 is just 2. And this again gives me 2 and 2 is just 4, and square root of 4 is just 2. So to simplify this, what I do is I circle all my groups of 2 of a kind, and then I take a value out from each of those. So again, square root of 4 is 2, or in other words, I think about, well, if there's 2 2's, that means the square root of that would just be 2. Square root of this would just be 2. So there's kind of like 2 2's on the outside of my radical sign. And then since this 3 is kind of hanging out underneath, like there's no nothing to pair it up with, it gets left underneath the radical. And so what I get here then is the same answer as I got above, which is 4 root 3. All right, let's try one more just to kind of practice. So let's do root 98. So again, if you're thinking of the largest perfect square that goes into 98, and some of you probably are pretty good at this, and some of you maybe are struggling a little bit. So I would have probably said, okay, 49, because 49 and 2 gives me 98. Since 49 is a perfect square, again, what it's really kind of doing is you're breaking it into kind of root 49 and root 2, I get 7 root 2, because the square root of 49 is indeed 7. If you didn't want to do it that way, so if you wanted to do it the other way, just to kind of show it one more time, you would do more of the prime factorization. So you might break this down into, well, in this one, it's actually the same thing, right? You would do 2 and 49, but let's say you didn't recognize that 49 was a perfect square. Or if you wanted to really break it down to the list, like prime factorization. This is why I get 7 root 2, is because there's a group of 7's in here. And so my final answer, again, would be 7 root 2. All right, the next thing I want to talk about is just rationalizing. And some of you are pretty good at this, and we've talked a little bit about this in class. But just to kind of, reiterate this again, before we get into like solving with the square and solving with quadratic formula, we want to make sure that we can kind of deal with radicals. And so what rationalize means is that there's no square root, or any root for that matter, on the denominator of the fraction. All right, so there's no square root in the denominator of the fraction. So let's do kind of a basic example. If I did 1 over root 2, what you do to get rid of this radical that's on the bottom of your fraction is you multiply by 1. In other words, I'm going to multiply by that exact same radical. So I'm going to multiply by root 2 over root 2. And what this does is it allows me to kind of scale up my radical or my fraction, but by doing that, I get rid of the radical that's on the bottom. And so this is kind of what I consider a legal move in mathematics, because what we're really just doing here, root 2 over root 2 is just 1. And so by multiplying by 1, I'm not changing the value of my problem. So if I would have multiplied by root 2 over 5, for example, I'm changing the value of my problem. I'm not scaling the numerator and the denominator up by something like the same thing, which means that I'm not going to have an equivalent value. Your answer here, so when I multiply this, I get 1 times root 2, which is root 2. Root 2 times root 2 is root 4, which is going to be 2. So this number here is the same exact number as this. These are equivalent. It's like just writing it in a different format. It's kind of like writing 1/2 and 2/4. They're the same thing. We're just scaling it up. And so this is what we call rationalizing, because we want to get rid of that radical on the bottom. Let me show you a couple other examples. We'll do one more that has kind of, let's have a number on top this time. It doesn't really change much. All we're going to do here is we're going to multiply the top and bottom by 1, which in this case is going to be root 5 over root 5. So on the numerator, I'm going to get 3 times root 5. And then root 5 times root 5 is root 25, or 5. If these numbers, since they're both outside of a radical, if those could be reduced, then you would reduce them. In this case, obviously, 3 over 5 cannot be reduced, so we're going to leave it as is. All right, let's see what happens if I have 2 radicals, a radical over a radical. You would approach this the same way. So in other words, you're going to get rid of this radical on the bottom. So I'm going to go ahead and multiply by 1, or root 3 over root 3. When you multiply radicals, as long as when you multiply radicals, you can multiply unlike radicals. What I mean by that is, like, you can multiply root 2 by root 3. And what you get there is root 6. Now, if you were adding those, you wouldn't be able to do that. But if you're multiplying, you can multiply radicals that have a different number underneath that radical sign. So this would give me root 9, which again is 3. Be careful, because sometimes, like this number right here, could be reduced. So remember how we did at the very beginning where we reduced our radicals? There will be situations in which, like, this number could be reduced, and then you would have to kind of simplify this one more time. Let's look at one more example. How about I did root 5 over 2 root 3? So the mistake that I generally see here when it comes to rationalizing this particular problem is that I'll see people multiply by 2 root 3 over 2 root 3, which that is technically okay because you're still just multiplying by 1, but it's unnecessary to multiply by the 2 because all you're really doing there is causing yourself to have to simplify again later. So you really just want to get rid of that root 3. So let's just multiply by root 3 over root 3. By doing that, on the numerator, again, you can multiply those together. I get root 15. And on the denominator, let's think about what this would equal. I have this 2, and then root 3 and root 3 is root 9, or in other words, 3. And then you just multiply those together. So it's like saying 2 times root 9, or 2 times 3, which is 6. Again, you would want to check to see this can't be reduced. 15 is 3 and 5, which there are no perfect squares in those, so we would have to just leave it as is. All right, let's talk about one more kind of form of factoring, and that's with that conjugate. And I know I talked about this in class. A conjugate is basically the same thing as rationalizing, except when you're rationalizing an expression that's a binomial. So let me show you what that looks like. So if I had 1 over 1 plus root 2. And so what that means is this is a binomial now, which is different than if you had this multiplied together. You can't just multiply by root 2 over root 2 because I would not end up getting rid of the radical that's on the bottom of my fraction. So in order for us to get rid of this radical, we multiply by a word called the conjugate, which basically just means this binomial, I'm going to multiply by its opposite. So if it's 1 plus root 2, I'm going to multiply top and bottom by 1 minus root 2. The reason we do this kind of stems back to when we did difference of perfect squares. So I'm just going to kind of remind you of what we did there. So remember when we had difference of two squares, right? So I've had x squared minus 100. To factor this, you would square root the x squared, and then you would square root 100. One's negative, one's positive. The reason why this pattern, okay, so I would give you any group of two parentheses that have the same factors, so x and 2, but one's negative, one's positive. If I FOIL this out, what's going to happen is my middle terms are always going to cancel. And so that's ultimately what we're trying to do here with this conjugate. I'm multiplying, I'm going to think of this as foiling. I'm going to multiply this by 1 plus root 2 times 1 minus root 2. And what's going to happen is these are the same values, so that middle term is going to cancel. So let me show you what that looks like. So on the numerator, I'm just going to get 1 minus root 2. And if I FOILed this out, I would get 1 times negative root 2 plus root 2 minus root 4, which is 2. So notice that those middle terms cancel out. So any of the radicals now are gone. And I just have 1 minus 2, which is negative 1. Generally, you will not see a negative on the bottom of a fraction. And so in most cases, what you're going to do is you're going to kind of simplify this. So you're going to go 1 divided by negative 1, which is negative 1. And then you're going to go negative root 2 over negative 1, which is positive root 2. This and this are equivalent. It's just we're kind of simplifying that to get rid of that negative 1 off the bottom of your fraction. Let me do a couple others. Let's do another conjugate. Let's do root 3 over 2 minus root 5. So the conjugate here would have to be 2 plus root 5. So on the numerator, we're going to go ahead and distribute this root 3. So root 3 times 2 is 2 root 3. Be careful there. You're not multiplying that 2 by 3 because one's a radical, one's a whole number. So numbers with numbers, radicals with radicals. So root 3 times 2 gives me 2 root 3. And then root 3 times root 5, that's positive, right? Because they're both positive. Since they're both radicals, you can multiply them together to get root 15. On the denominator, kind of the shortcut way, now that you know the middle terms are going to cancel, all you're really doing then is multiplying the first two numbers together, which is 4, and the last two numbers together, which would give me negative 5. All right, let's just simplify a little bit. So 2 root 3 plus root 15 over negative 1. And then I'm just going to rewrite it as negative 2 root 3 minus root 15, just to kind of simplify it up a little bit. All right, let's do one more example. Let's do one that has kind of a binomial in the top and a binomial in the bottom. Okay, so again, it's just various levels of problems. We're doing the same process over and over again. So we're going to multiply by the conjugate. So I'm going to multiply by 2 plus root 6. FOIL, okay? So this is a binomial times a binomial on the numerator. So you're going to have to multiply out. So 1 times 2 is 2. 1 times root 6 is positive root 6. Root 3 times 2, again, you can't multiply numbers and radicals together, so it's like 2 root 3. It's kind of like next to each other. And then root 3 times root 6 is root 18. Over. And then since these are conjugates, the middle terms are going to cancel, so this gives me 4. I'll just write it over here. And then negative root 6 times root 6 is negative 6. All right, let's simplify this a little. So I have, on the numerator, I have 2 plus root 6 plus 2 root 3. None of those can be added together because they don't have the same radical. The only radicals that can be added together would be if this said root 6 and this was root 6, then I could add these together. This root 18, this is one I want you to reduce. So remember, root 18 is really just 9 times 2, right? So I can reduce root 18 to 3 root 2. So be careful here. Like this is, again, like I was telling you before, this is one where I would like you to reduce one. And then 4 minus 6 is negative 2. A lot of times, so yeah, okay. So then on this one, what you could do is you could divide everything by negative 2 if you wanted to. I'm okay if you leave it in this format, actually, at this point. If you wanted to multiply through by a negative and get a negative off the bottom of your fraction, just put the negative on the top. That's fine as well. But at this stage, I'm okay with leaving it like this. All right, let's talk one more thing. I want to talk about solving, but using what we call the square root method. So just kind of wanted to reiterate how to solve kind of using radicals. So we're going to do a bunch of solving, and this is just one way of solving, okay? So this is just one kind of process. So the square root method, we generally use this for two different forms. We use this for vertex form, or when an equation has no x value. So I'll show you some examples of both. So for example, if I had y equals 2x minus 1 squared minus 4. So you've done this when we talked about graphing in vertex form, right? When we talked about graphing in vertex form, you had to find x-intercepts. Well, x-intercepts is the same thing as solving. So what I'm going to do is I'm going to set y equal to 0, because when we solve, that's what we're going to set y equal to 0. And then we're solving for x. So when it's in vertex form, I want to remind you again, not to distribute this out, okay? We're going to isolate this x minus 1 squared. In other words, let's get rid of the negative 4, let's get rid of the 2. So I'm going to add 4 to both sides. Whoops, not a radical. It's supposed to say x minus 1 squared. And then I'm going to divide both sides by 2. So now that I've got that binomial squared by itself, so this piece by itself, now we're going to square root both sides to get rid of that squared. So I get plus or minus root 2 equals, don't forget your plus or minus, and then this just gives me x minus 1. Finally, what I'm going to do is I'm going to add 1 to both sides, so to get x by itself. So I have 1 plus or minus root 2. I'm going to leave this in radical form. If I were graphing this, I would change those into x-intercepts. And so this is actually two answers here, right? So because of the plus and minus. So you would do 1 plus root 2, like if you were putting this in your calculator, and then you would do 1 minus root 2, and those would be your two x-intercepts. So if I did that, I would get numbers like 2.41, and I would get negative 0.41. And so obviously if I was graphing it, I'd want to write them as decimals just so I can see approximately where they're located. Another example, so that's vertex form. One of the ways I want you to do the other kind of example of using vertex form is when the expression has no x value. So let me show you. So look at my equation here. I have x squared minus 10 equals 14. Notice that there's no x, okay? There's an x squared, but there's no x. So whenever that occurs, I want us to remember to use the square root method, which again, just means we're isolating whatever's being squared. Just like we isolated this x minus 1 because it was being squared, we're gonna isolate x. So I'm gonna add 10 to both sides. So now we're just gonna square root both sides. But now I want you to remember all of your practice with radicals. So we're going to reduce this radical. And so I get, let's see here, goes into 24, 4 and 6. So 4 is a perfect square. So my final answer is plus or minus, the square root of 4 is 2 root 6. And that would be my final answer. If I wrote them as decimals, again, if I was going to graph this, I would just put in my calculator 2 root 6. And then I'd put in my calculator negative 2 root 6. And those would be my two x-intercepts. In terms of making sure that you're understanding kind of the square root method, again, the two forms that we use this for are vertex forms. So again, looking like this, where we have kind of that H and K scenario. And then when you have no x value in your equation. So again, just the x squared and then constant terms. All right, that's it for now. What we're gonna do is we'll practice some other solving in the next video, and then we'll be close to being done. All right, that's all for now. Bye.